Hi, my name is Rodrigo Bissacot and I'm from the University of São Paulo, Brazil. This talk is about the generalization of the notion of DLR measure from the probability setting to the sigma finite setting. It's a joint work with Elmer Beltran. He is now in a postdoc position in Universidade Católica do Norte in Chile, and also with Eric Endo from Shanghai. Both are former students from our group here in São Paulo. The main reference is this preprint, which you can find in archive. The results actually are most containing in the PGTs from Elmer. The PGT is in Portuguese, but essentially the main results are you can find in this preprinting archive. For more information about our group and what we are doing here in São Paulo, you can look in our website of the group. And essentially, we are working this interface between ergo theory and mathematical physics. In this talk, I will keep always my configuration space as a contact Markov shift, which means that I have an infinite matrix of zeros and ones, which tells me which are the sequence allowed. The alphabet is the natural numbers, and I have the usual cylinder sets, and I consider the Borel sigma algebra generated by these sets. And one important notion here is this sigma algebra of the coordinates from some n to infinity. Let's say I take the sigma algebra generated by the random variables associated to the position n and bigger than 1. This corresponds to outside of the box in the usual definition of the DLR measure. So if I have a sigma finite measure defined in my Borel sigma algebra, and I have a potential, I will assume more regularity after, but for now, just measurable is okay. And I say that a measure here is a DLR measure for this potential if the measure satisfies the DLR equations, which means that for any n, I consider the conditional expectation respect to outside of the cylinder, and I impose that this conditional expectation should satisfies this equation. The right side is the usual specification from Gibbs theory. In the denominator, I just fixed the x and run for all the possibilities inside of the cylinder. And the phi n is the usual Birkhoff sum. So for this setting, this is the DLR equation. Here, since I am in a semilattice and not in Z, I can use the Whole operator. Basically, is the main tool when you consider the semilattice and not the complete lattice Z. So I will avoid the technicalities about okay, what exactly the hypothesis to the potential and the function right now, but you can look in the article. But this is the main tool here, let's say. And after you define your Whole operator, you can try to find the dual objects, which means measures. But here you don't have the His representation theorem because the space in general is not locally compact. You have a special collection of quantum Markov which are locally compact, but in general and for our examples, most of them are not locally compact. So you have to define this duality in this weak sense, let's say. The main facts about this theory which is a generalization of Ruel and Bowen did in the 70s, are the following. The eigenmeasure, when you find the eigenmeasure, you have to find the right conditions to find the eigenmeasure. Any eigenmeasure is a DLR measure. But in this non-compact setting, the eigenmeasures are not necessarily a probability. So you can if you put some right some suitable hypothesis on the potential in the countable Markov shift also, you can find finite eigenmeasures, but sometimes they are only sigma finite. So now, as you see, so the sigma finite DLR measures already exist actually, but they are in this setting of thermodynamic formulas, which more people from ergo theory works and not exactly people from mathematical physics and probability community are working there. And if you look in this generalized Ruel, Perron, Frobenius, Stirner, proved by Henri Sarrigi, he gives conditions to the existence of these measures. So we have already a definition of sigma finite DLR measure and know some theories that says to you when these measures exist. One important shift on this setting is the renewal shift, which means it's the only possible allowed connections between the symbols are this one. So if you have the symbol 1, you can go to any other. But if you are in the 3, you have to go to the 2, and if you are in the 2, you have to go to the 1, and so on. For this particular shift, if you consider a potential which is regular enough, so you have this kind of result that we see in many models also in statistical mechanics, since Fisher, for example. And when you have an interval when you are able to find a conservative eigenmeasure for the potential beta phi, and after this you don't have your eigenmeasure anymore. The pressure is analytic on this first region of beta, and after is a linear function. The pressure is continuous, but it's not analytic in this critical point. So this is kind of a phase transition in the sense of lack of analyticity of the pressure function. But look, as I said before, okay, you have the eigenmeasure, but you don't know a priori if this measure is finite or not. So this was our main motivation when we start this project. And what we were able to prove is exactly this. For this shift, which is one of the most understood on this theory, we are able to prove that if the potential is regular enough, I mean weakly holder, this is totally general. You see, it's not a example. This always happens for this class of for this shift and for this class of potentials. The eigenmeasures is always finite when you have a high enough temperature, which means beta very small. And after a critical beta, the eigenmeasure become infinity. So since I already said the eigenmeasures are DLR measures, this is a jump from a set of finite DLR measures to infinity DLR measures. And we know when this phase transition in terms of the volume does not exist. Exactly if you impose that the first variation of the potential is finite, so you don't see this, and the measure is always a finite DLR measure. This was our main contribution. We studied also some when the DLR measures are equal to the conformal measures to the eigenmeasures, but you can look this in the article. After this, we try to go further and see what we can go for more general shifts or or what we can find. And this is just a couple of examples where you have you have case where you find a critical beta which is different from the beta until you have the eigenmeasure, or you can have only one type of measure during the entire interval. You have also another shift which is considered on this thermodynamic formalism setting, which are the same graph, but you take the inverse direction on the edges, so some kind of reversal linear shift. This shift is locally compact actually, and but look, this is a nice example to see how let's say how complicated things can be if you consider matrix, the incident matrix as a parameter, and the potential and everything. For example, the Dirichlet measure on this point 1, 2, 3, 4, which is allowed now, is a DLR measure for any potential. So which means that if you don't consider the full shift, you consider shifts that when you can change your matrix, maybe you can find some surprises. This is based on an example of Ofer Schwartz in a paper of last year in Communication Mathematical Physics. And for this class of shifts, we have a couple of results, not a complete one as in the standard linear shift, but we have conditions to say when you don't have a volume time phase transition. So this is a couple of examples, but these conditions are not sharp. So we have an example where you have phase transition, but we have an example also when we don't have phase transition, when you don't satisfy the conditions of the previous term. So that's it. We believe that this could be a very good direction to try to extend the theory, in the sense that when we are trying to look for DLR measures in some models, we don't put as an a priori hypothesis the finiteness of the DLR measure. So maybe we can find something interesting in the space of the infinite DLR measures also. So thank you. Enjoyed the symposium.